to realize. On your exam, you will be given an activity series, a shortened version of the activity series. So this is a good reference coming from exam 2, particularly the feedback that I got. Exam 3, practice exam, is posted. It's on Canvas. Download that. Start looking at it, please. I'd like to see scores go up. Okay? If you look at that first page, you will see a shortened version of the activity series. Okay? So it's not going to have all of them, but it'll have all the elements necessary to answer questions within the exam. All right, so you need to be able to interpret and use that. That interpreting and using it should get you to realize that the last two reactions don't actually occur. And that the first two do go forwards as written, yes. Okay? Your textbook goes through and starts adding in this active metals and water. There are some metals that when you add them to water, they go through and do the same type of reaction. Okay? The reason being is that those metals are so active that even a weak hydrogen source like water will allow them to react. Okay? So if we look, actually I removed all that example. So if we look at our activity series, you'll notice that hydrogen does show up within the activity series. But when we're looking at hydrogen, it is typically hydrogen coming from, not coming from water typically, actually. Yeah. It's water, or it's hydrogen coming from something like this species, which happens to be an acid. So if we have an acidic hydrogen, which for some dumb reason we have not defined yet, don't stress on it. Okay? If we have an acidic hydrogen, that's typically the hydrogen that's referenced within the activity series. Okay? So it has to be, for lack of any better descriptor at this point, an acidic hydrogen. When we look at H2O, is that defined as an acid? No. How do you know it's not defined as an acid? What is your definition of an acid right now? It has a, whoops, come back here. I didn't do that. Your definition of an acid is it has hydrogen and it has a Q with it. Okay? That is a horrible definition, but it works well enough for what we're trying to look at right here. So when we go through and look at water, it does not, or it does have the hydrogen, but it does not have the AQ. Okay? And again, horrible definition. We will make that definition better later in the semester. But water does not satisfy that acid requirement. So if we looked at this reaction, we might say, well, this doesn't supply the acidic hydrogen, so it shouldn't do this single replacement reaction. It turns out that there are some metals that are so reactive that they will react with the hydrogen from water just as quickly as a hydrogen from an acid. Okay? This is this kind of weird exception thing. You are not required to have that memorized. It's just something the textbook addresses. I just want you to be aware of it. We can take these metals and we can drop them into water and we do see a violent reaction. Those metals tend to be your group 1 and group 2 metals. Where's sodium? Group 1. Where's calcium? Group 2. If we go through and take a look at our activity series, what are our most active metals? Lithium, potassium, which are in group 1. Calcium, which is in sodium, 1. Magnesium, 2. Okay, our most active metals tend to be in those first two columns. So those, when added to water, do react even though it's not a hydrogen source. Or sorry, an acidic hydrogen source. Okay? So you may see questions like that in the textbook. I won't ever explicitly ask it in an exam. How many of you have read chapter 17, or at least read those first couple sections? Okay, a few people. Those few people may be okay with this. The rest of you, this is going to be rough. Okay? What we are looking at now is oxidation and reduction. If we went back and looked at these reactions, let's take a look at what we've referenced as charge. What is the charge on sodium in the reactant? Charge is always written in the upper right-hand corner. What is that charge? 0. Those of you shouting out +1. Sodium ion is indeed positive charge. How do I know I'm not looking at sodium ion? There's no charge written in the upper right-hand corner. Okay. What is the charge on sodium in the product? Okay, so you're again referencing that there's no charge written in the upper right-hand corner, so you're calling it 0. Unfortunately, that is no charge on sodium hydroxide. Not sodium, sodium hydroxide. What is the charge on hydroxide? What charge does sodium have to be to make sure the charge on sodium hydroxide is no charge? +1. In the course of this reaction, sodium went from a 0 charge state to a +1 charge state. How can we change the charge? What has to happen to that atom of sodium? It has to lose electrons. Okay, I did hear someone shout out gain. Okay, the only thing it could potentially gain would be protons. But if it gained protons to become positive, it's not sodium anymore. It would become magnesium. So when we're changing charge states, the only thing we can change are the number of electrons, not the number of protons. This does become weird because the charge on an electron is -1. If we remove a -1, we've become positive. A loss of something makes me positive. A loss of debt does mean you have net wealth. Okay? So you have to be careful with this. This is where that mathematical symbol of a negative messes with all of your calculations. Okay? So be very, very careful when you approach this. So in these reactions, we are changing that quote-unquote charge. It turns out we are not actually changing the charge on the atom. We are changing another property of an individual atom. Okay? That property is known as an oxidation state or an oxidation number. It is the balance of protons and electrons in an atom, whereas charge is the balance of protons and electrons in a unit. Well, that unit could be a molecule. It could also be an atom. So in some cases, your charge and oxidation state are the same thing. Okay? But be careful. They mean entirely different things. Oxidation state and number is assigned to an atom. Charge is assigned to a unit, which can be anything, a molecule. It can also be an atom, depending on what we're referencing. What was your question? Just saying that again. So, if we went through and looked at this, let's go through and work it again. What is the charge, quote unquote, for our calcium in our reactant? It is a 0. I know that you're wanting to jump on that charge. You got to be careful. In the product, it is +2. It has to balance out the charge from our hydroxide. What is the charge on hydrogen? This is a bit of a weird one, and you should be having a pause here. Okay? We've never actually told you how to determine the charge from the hydrogen. Okay? The only times that you've looked at trying to know charges are coming from ionic compounds. Is water an ionic compound? No. So how can we determine the charge for the atoms in an ionic compound? Okay? This is where our distinguishing comes apart. We don't. We determine the oxidation state. So all of those charges that we had you memorize were for ionic compounds. As soon as we move into covalent compounds, you have to now forget those charges that you've memorized, and you have to solve for it. And that becomes tricky. Turns out that the charge on that hydrogen, the oxidation number on that hydrogen will be +1. What is the charge on the hydrogen in H2? Upper right-hand corner. What does the charge on the hydrogen have to be to get a charge of 0? 0. Okay. The charge on the oxygen is interesting enough. It's actually -2. Charge on the oxygen and hydroxide. -2. Questions about anything that's put up there so far? Yes, you don't have the rule set, so you might have some questions here. Let's see what you got. Nothing? Really? This is easy? You guys are like, okay, this is cool. I should just skip the next 20 slides and just be like, okay, you got it?
Maybe more examples.
Okay, maybe more examples. So what we are referencing is our oxidation states. And in some cases, those oxidation states are the same as charge. Your state or number, I tend to use them interchangeably, applies only to an atom. So when I went through and assigned those, you notice that I've only highlighted atoms to assign those oxidation numbers. The charge will apply to a unit. Where does this overlap? What is the first unit? Is right there. The oxidation number for the atom within that unit is 0. What is the charge for that unit? 0. The charge is always specified in that upper right-hand corner, and it is 0. And it just so happens that the oxidation state or number ends up coming out to be the same. This is kind of this weird, odd balance. Okay? If we move to, say, the unit of this one, what is the charge on that unit? Charge is 0, written in the upper right-hand corner. If I now want to refer to the oxidation state, I have to refer to the oxidation state for hydrogen and oxygen, independent of each other, because the oxidation state only applies to the atom, not the whole unit. To determine the oxidation state, it is something you must calculate every single time. In certain cases, like in our very first example with the calcium, you look at that calculation and go, oh, well, that's easy, it's just 0. Okay, it's the same thing. That's because it's the only piece there. When we have other atoms included, that's when you have to start worrying about calculation. Well, how am I doing this calculation? Using a formula to determine the calculation. So on and so forth, and this must then equal whoops, made some quick mistakes here. The oxidation number for our atom this has to equal the overall charge. Does this formula look familiar to anybody? It should look really familiar. It should look almost identical to that formula that I told you that you should be using to determine the charges in all of your nomenclature rules. That's because it is the same formula. So if you went through and used the textbook formulation of crossover rule, you've now screwed yourself over for oxidation numbers. There's a reason that balance of electrons and protons is important. It applies right here. And when we talked about it in nomenclature, we referenced it as charge. It's not officially charge. It's the oxidation number for each of those atoms. When we sum all of the oxidation numbers for our atoms, that gets us our overall charge. If we go through and take a look at the calcium, okay, that very first one, if I want to figure out the oxidation number on that calcium, let's use this formula. How do we do it? The number of the atom. How many calciums are there? 1. What is the oxidation number for calcium? You always solve for it, so at this point we don't know it. It is X. What's the next atom? There isn't one. Okay, so I don't have to add plus. Whoops. I can just do an equals. This now equals the overall charge. What is the overall charge on that molecule? 0. What is the oxidation number? 0. There it is. Okay. What happens? Whoops, I don't want that eraser. If I now move to water. Well, we set up the exact same setup. How many hydrogens are there?
0.
What is the oxidation number for hydrogen? Don't know. Good answer. Plus 1. What's the oxidation number for oxygen? Don't know. This has to equal the overall charge, which is 0. One equation, 2 unknowns. Can you solve it? Officially not. We can potentially do some guess and check on this. Just a second. To make it look like a 0. Or make it not look like a 0. Make it look different from an O. Which is what I think you were just telling her. Okay? How did I go through and solve this? There's more rules. Okay? You need to know some rules to allowing you to solve for the oxidation numbers for everything. The more important rule, or one of the most important rules, 3A, oxygen will have a -2 oxidation state, which means in that previous equation, y equals -2. I can now go through and solve for x. So here's all these rules the textbook has kind of highlighted and said is super important. I would make the argument that most of these rules can be derived from knowing the sum of the oxidation numbers, that's our equation, and some of those rule 3s. In particular, oxygen being the most important one. Hydrogen you can almost always solve for, so not a huge issue. And knowing your halides are -1. Okay. If you know those, you can solve for pretty much any oxidation state. So let's take a look at that water again. We said 2 hydrogens times its charge plus 1 oxygen times its charge has to equal 0. We just said, according to our rule, 3A, oxygen will always have a -2 oxidation state, which means Y is -2. Can you solve for X for me? Careful. Can you solve for X for me? No. 2x minus 2 equals 0. That was not the right button. So let's try that again. 2x equals 2. X equals plus 1. What's the oxidation state for hydrogen? Plus 1. What was one of those rules? Hydrogen's a plus 1. Okay. Like I said, you don't have to have hydrogen being a plus 1 memorized because it directly solves for out of your questions. Is that?
Well, also, can you make the other slide?
Yeah. Oh, you're just writing down the rules? Okay. Important rules that you should absolutely have memorized. Rule 4, which you already memorized from doing all the nomenclature like the way I asked you to do it. Rule 3A, Rule 3C. Okay. Those are the critical ones that you should absolutely commit to memory. The rest of them kind of just fall out of solving the problems according to the rule sets you already know. Okay? Since it looks like you're copying that down, I should probably pause and give you a second to write it down. Charge the number written in the upper right-hand corner of all formulas. Every single compound we ever give you, you know the charge because we have to give it to you. Okay? The oxidation state is something that at this stage I would say you should always calculate. Even if you're like, well, that's dumb. I don't care. Do it anyway. It's part of that get angry thing. So let's take a look at the first problems. And I definitely circled these out of order. Let's look at that middle one. Copper ion. What is the charge for that unit? How do you know that? Upper right-hand corner, it says +2. Okay. Hey, look, I guessed that right. Let's say I went back to copper. Copper metal. What's the charge on that one? Dang it. Nothing's written in that upper right-hand corner. It is 0. What is the charge? Of course, now I start clicking like crazy. The charge on nitrate? -1. Charge on sulfate? -2. Always written in that upper right-hand corner. You can identify it, it's given to you. Some cases it's not explicitly given to you. Okay, so let's come up with an example here. What is the charge, you ready for it, on hydroxide? What's written in the upper right-hand corner? Well, nothing, because it's not a formula. If you're given a formula, you're given the charge. You have to convert hydroxide into a formula. What is the formula for hydroxide? OH minus. What's the charge on hydroxide? -1. You still have to know those complex ions that I told you to memorize. Okay, that's your nomenclature rule. If we move to our oxidation states and now try and go through and calculate these. What is the oxidation state for that first one? Copper metal. Okay. Thank you for shouting out the answer. I do kind of appreciate that. But this is one that we want to solve. So damn it, we're going to solve it. How many coppers are in that unit? What is the oxidation state for copper? Don't know. What's the next element in that unit? Nothing. Okay, so this has to then equal the overall charge. What is the overall charge? 0. What is the oxidation state for copper? 0. You've now solved it for that first one. Whoa, come back here. Don't look at all that. Oxidation state for copper ion. +2. Okay, with it there only being one element there, the oxidation number must be equal to the oxidation state. It directly solves out of that formula. Okay. What is the oxidation state for nitrogen? I'm assuming the silence is because you're frantically writing down some work to say what that number is. I am glad that nobody shouted out -3. What is -3? It's the charge on nitrogen in an ionic compound. Is this an ionic compound? No. Okay? So it's not looking at the charge. We now have to determine the oxidation state. For those of you a little bit panicked on this, how many nitrogens are there in that compound? What is its oxidation number? Careful, don't solve it. We don't know. Plus, what's the next element? Oxygen. How many oxygens are there? What is the oxidation number for oxygen? -2. How do we know it's -2? This is one of the rules you have to have memorized. Oxygen will carry a -2 charge. What's the next element? Nothing. So this then has to equal the overall charge. What is the overall charge on the compound that's containing nitrogen? -1. Can you now solve for x? Yep. And you'll solve for x and get x equals, now whoever shouted it out over here, +5. Our formula must equal the overall charge. What is the overall charge on nitrate? Upper right-hand corner. It is always given to you. The charge on nitrate, -1. Okay? Written in that upper right-hand corner, what do we have? A negative sign. That is our overall charge.
So then why do you do all that?
Why do we do all what?
Okay, so you write all of that and you're supposed to equal what it gives you.
Yep.
So if it gives it to you, right?
What it gives you is the overall charge. It did not give you the oxidation state for the nitrogen. Okay? Why do we need the oxidation state for the nitrogen? That's the next big mess of stuff that we're going to talk about. But before you can get to that point, you have to be able to determine the oxidation state. If you can't determine the oxidation state, the next sequence of information is completely meaningless. Okay? So yes, it does stack.
So the oxidation state is 5, right? Or when they're
The oxidation state of nitrogen equals +5. Yes. The only way we determined that was by going through and solving for it. What is the oxidation state for oxygen in sulfate? How do you know it's -2? You said that awfully quick. It's one of the rules that you have to have memorized. Oxygen will be a -2 oxidation state. Okay. What is the oxidation state for sulfur? In sulfate. Spend a second, try and go through and solve that. If you've got +6. Okay. Got another good question out of this. What is this showing? Okay. If I just look at sulfur and I say, okay, what is the oxidation number for sulfur?
It's not a fixed number.
It's 0. It has exactly, 16 protons, 16 electrons. Its balance of protons and electrons is exactly even, which means it exactly comes out as a 0 difference between the protons and electrons. What happens if I now put that sulfur near another element? What can happen?
The balance of electrons.
It can, before we even get to the balance of electrons, but you're right, it forms a bond. How does it form a bond? By sharing electrons. Are those electrons shared perfectly even every single time? No, that's why we have ionic bonds, why we have covalent bonds, why we have polar covalent bonds. So the electrons are unevenly shared. How do we decide how they're unevenly shared? Which atom takes most of the electrons in the bond? The more electronegative one. Okay, so all of the Lewis structures and all that theory is looking at how two atoms share their electrons to make a bond. We now no longer have that element anymore. Its chemical properties have changed because that other atom is either potentially giving it electrons or taking electrons away from it, which is now going to change its balance of protons and electrons. The only way I can determine that change or that balance is by going through and looking at those oxidation state rules. Okay? That's what we're ultimately looking at by determining these oxidation states. Sulfur is coming out as a +6 charge. Which element is more electronegative, sulfur or oxygen? Oxygen. Oxygen. What is oxygen going to do? Take electrons away from sulfur. Well, if sulfur loses electrons, what happens to its charge? Or sorry, oxidation number. It becomes positive. What did we say the oxidation number was? Positive. The magnitude of it being +6 versus +1, +2, +4 depends on how many oxygens are involved and how those oxygens are interacting with it. This formula simplifies that down so that we can see that individual balance within it. This gives us an idea of what is happening to the sulfur. Okay? Questions? Deep breath, let's make it a mess. What we'll now do is take this information and translate it into a reaction. So we've got a big, complicated, nasty-looking reaction up there. which you don't know how to classify, so don't worry about classifying it. Okay. What we should be able to go through and do is look at the oxidation number for every single element on the reactant side and every single element on the product side. If our reaction was built up correctly, if iodine shows up in the reactant, it should also show up in the product. So our equation should be roughly balanced as far as our elements are concerned, and we can go through and now look at the oxidation numbers. What happened to iodine to go from a reactant to a product? Went from a +5 oxidation state to a 0. How does it go from a +5 to a 0? It had to gain electrons. So what occurred? Gained electrons. Right? Electrons, remember, are these tiny, nasty, vicious, unstable little creatures, which means they cannot just appear out of nowhere. They have to come from somewhere. Something else must provide them. So as soon as I find that a species gains electrons, somewhere else in the reaction, what had to happen? Something else had to lose electrons. So let's take a look at oxygen. What happened to the oxygen in the course of the reaction? Went from a -2 to -2. So what happened to the oxygen? Nothing. Okay. So it was not the source of electrons. What happened to the carbon? It went from a +2 to a +4. To go from a +2 to a +4, it had to become more positive. To become more positive, what did it have to do? Lose electrons. Where did those lost electrons go? They can't be just lost out into space. They have to be picked up. What picked them up? Iodine. For the reaction to occur, I have to have both the gain of electrons and the loss of electrons happen simultaneously. Otherwise, the reaction does not work. Okay? Which is why we end up going through and referencing these reactions in the next state or the next naming system that we come up with. Gaining of electrons and loss of electrons is too tedious to go through and say each time. So we come up with a special name for them. Okay? For the one that gained electrons, what happened to its oxidation number? +5 to 0.
It's reduced.
It decreased, or it was reduced. Gaining of electrons is referred to as a reduction. Okay? It's kind of nice, it matches the oxidation numbers. What happened to the oxidation numbers for carbon? Pointed over here too long. I went from a +2 to a +4, so it was increased. Okay? Or it was increased adduction. Okay? We don't have a nice word for that. What we end up calling those ones is oxidation. Okay? Why do we reference it as oxidation and not increased adduction? Beyond the fact that increased adduction just sounds stupid. Okay? What happened to the carbon in the course of the reaction? What was it bonded to on the reactant side? How many oxygens?
2.
On the reactant side,
Oh, sorry.
1. On the product side, 2. What happened to the number of oxygen bonds to our carbon? It increased. Okay? Or we oxidized it by adding oxygens. The definition or the term for redox reactions or reduction and oxidation ultimately came from the oxidation side of it. We noticed oxidation was a common issue. Okay? Where might we have noticed oxidation being a common issue? Rust. All of the metals that we put together moved through the Bronze Age and all those fun things. We noticed this weird corrosion that was happening, destroying our metal weapons, destroying our boats. Okay? And we noticed that that happened when we exposed our substance to air. What did we decide was in air? Oxygen. As soon as we removed the oxygen, we didn't get this reaction. So what we did is named that reaction according to the species that's doing the chemistry, which was oxygen. So we saw oxidation. It wasn't until later that we understood something about the balance of protons and electrons that we could then start to look at what's happening to the oxidation states. And that's where reduction came from. So you need to remember that in the course of the reaction, it's not just knowing your oxidation states, but it's then applying that to a reaction. If we lose electrons, that is oxidation. If we gain electrons, that is reduction. Yes?
It's not like totally obvious that iodine gained 5 electrons.
That is true.
Where did that happen?
So within the course of the reaction, you don't need to know, particularly for this equation, not an easy one to see how it's gaining those electrons. We'll look at some simple examples of that. This is why I would completely ignore the textbook when it comes to balancing redox reactions, because what it's looking at are vastly complicated reactions. This is one of those cases. Exactly how the iodine is gaining those electrons, you are not responsible for, and you do not want to be responsible for it. Okay? How can you help remember loss of electrons is oxidation? I hate the oil rig. Leo, which happens to be another name for lion, which is a giant cat. What do cats do? There's even a hint on the board. Wait a minute. They growl at you. Yeah, big cats. Lion's a big cat. Growls. Leo the lion says grr. Right? Come on. As opposed to really oil rig, oxidation is loss. Loss of what? Okay? So all it says is oil. Oxidation is loss. What am I losing? Right? It doesn't even say in the name. Leo says grr actually tells you what's happening. Okay? So 2 ways you can memorize it. Apparently Leo says grr is a very rare one at this community college. Everybody seems to know oil rig. Okay? I've started to make some converts because I think Leo says grr more people like. It's funnier than oil rig. Okay. More green than oil rig. There we go. Some people laugh. One last thing to throw as a nice curveball on this. So when you're going through and looking at a reaction, now what you have to do is classify all of those 5 that we looked at before. Some of those can be what's referred to as a redox reaction. You'll notice that we don't just call it reduction, we don't just call it oxidation, we call it redox. Why have we shortened it into one word? We're lazy, and it's another big reason. Can I do the reduction by itself? No. Every time I do a reduction, what else has to happen? Oxidation. So I could go through and say, well, it's a reduction and oxidation reaction. That's really tedious. We can combine it all into one phrase, redox, that then necessarily implies that both of those have to happen at the exact same time. Okay? So look at your reactions, decide, is it reduction and oxidation? How do you decide? Oxidation numbers. If you can't figure out the oxidation numbers, you can't determine redox. Okay? You do not have to do it for every single equation. That is exactly correct. So oxygen was our primary discoverer of our redox, if you will. It does not mean oxygen is always involved in a reduction and oxidation reaction. It is typically, but not always. Okay. If that was not confusing enough, our latest curveball within this, we introduced this term of an oxidizing agent, also known as an oxidant. Okay, so if you're reading through a question and you see ing or ant, you should mildly panic, potentially even just skip the question because you know it's going to be confusing and you're going to get lost. Just fine. Okay, if you see either of those 2 endings, you should panic a little bit. Okay, reducing agent or reductant. Notice in both cases you see the ing and you see the ant. What is an oxidizing agent? An oxidizing agent is something that stole electrons from another compound. It caused another compound to be oxidized. So if I'm the oxidizing agent, Shay here is now oxidized. If she's oxidized, what happened to me, the oxidizing agent? I was reduced. Okay? So you just barely go through, determine your oxidation states, and you decide, okay, this species was oxidized, and then we ask you reducing agent. Okay? So you've got a lot of back and forth to go through and apply. As soon as you see these agents, these are doing the opposite thing of what their name is. An oxidizing agent was itself reduced. A reducing agent was itself oxidized. Okay? We reference these species as agents because we can classify certain compounds as being really good at being reduced or really good at being oxidized, which means if I put them near anything else, okay, something that's really good at being reduced, meaning gaining electrons, is really good at stealing electrons from another compound. Well, if I've got a shelf of compounds lined up and I put a reducing agent next to an oxidizing agent, one of those species is really good at stealing electrons, the other species is really good at giving them up. What happens? Poof! Big old massive reaction that we don't want to mess with. So we classify our compounds according to their reductive and oxidative abilities. This is your oxidizing agent and reducing agent. Okay? Be aware that that term can float out there. It is very confusing to work with. It may help if as soon as you see oxidizing agent, you would write above it reduced. What does reduced mean? Come on. Oxidizing agent was reduced. You look at an equation, it doesn't just scream out, oh, I'm reduced. What do you have to do? You have to look for the species that gained electrons. By writing that information down, you can now go to your equation and determine the oxidation numbers. Once you've got your oxidation numbers, you can then backtrack through all of your notes to solve the answer for the question. Clear as mud, right? So let's do some questions. Identify the oxidation states for every element on the reactant and product side for all three equations. Also identify the oxidizing agent and the reducing agent. And the species that was oxidized or reduced. Don't cheat.
What is the proper form for writing these down?
What do you mean?
I can just write it over my paper
Yeah, so you just write the first equation, and underneath it you could say 10 plus 2, oxidation state was plus 2. So you can just say ox number. Let's give you some kind of format, I guess. And actually, let's color code that.
That's a partial charge notation, right?
No,
Oh, it looks like it.
that's just because I'm sloppy handwriting. It's a good thing I'm wrong. We will go through and talk about this again on Thursday. But what you should go through and do is work through it on your own, and you should be coming up to these conclusions. Okay? So on Thursday, we'll go through it again, and we'll work through each of the individual steps on how we process each of these. I'm going to real quickly run through in about 3 minutes a real quick idea on what's happening within balancing in what's known as the half reaction method. I'm not spending a whole lot of time on it because it's really just going to be one question on your exam, and I don't want you panicking too much on it, and I don't want to waste time on it because of that. Okay? So let's go through and look at that balancing issue. In some cases, balancing may be obvious. In other cases, it may not be. If we look at this equation, how could we balance it? Put a 2 in front of H plus, and guess what? It's now balanced. Relatively straightforward. Other times, it may appear trivial, but it is not. So this equation looks kind of familiar, right? We just did this. Is this equation balanced? See, tin and tin, how many tins? 1 and 1, so, okay. Iron and iron, 1 and 1, so we might say it's balanced. The unfortunate thing with redox is the other thing that is moving around is not atoms, but is also the electrons. And how do we tell that electrons have moved? By looking at the charge. The overall charge on the reactant side is what? +5. The overall charge on the product side is +6. Which means it is not balanced. Okay? If the charge does not balance, then my electrons do not balance out. My reaction has failed. If I said the sum of my coefficients was 4, I get the wrong answer. Okay? So there are certain cases where balancing redox reactions is not just natural, oh yeah, we just balance it like normal. We also have to evaluate the electrons, and this is where it gets tricky. To go through and balance the electrons, we need to be able to see them so we know how to appreciate how they're moving around. Okay? So to go through and see them, what I'm going to do is split this reaction. I'm going to split it into what is known as the half reactions, where one half is the what? The half, not a bad answer, is the oxidation reaction. And the other half will be the reduction reaction. Okay? So what we'll do is now split this out where I've looked at my reduction. It's iron +3 going to iron +2. My oxidation is iron +2 going, that's not iron, tin +2 going to tin +4. So what I'm going to do is balance each of these half reactions first. Okay, well, iron +3 to iron +2, is the charge balanced? No. So how do I have to balance it? Okay, coefficients, there's no coefficients to change. It's one iron, one iron. What I'm going to introduce now are those nasty, extremely unstable species, electrons. To balance that first equation, I need one electron on the reactant side. What charge is an electron? -1. Plus the charge on iron gives me an overall charge on the reactant side of +2. What is the charge on my product side for the reduction reaction? +2. Are my charges balanced? Yes. So we're now adding electrons to either reactants or products to balance the charge on both sides of the equation. For the tin equation, you'll notice that we need to add 2 electrons. Why do I need 2 electrons? To make sure that the charge balances out. So it would be +2 and +2. I can then add my 2 equations together. Just like I separated them, I can now put them together. When I put them together, what do I get? Well, the 1 electron on the reactant also showed up as a product, so it can cancel one of those. And if I look at my overall equation, I've now produced 1 electron. Everybody okay with that addition? Ish, okay, I can accept that. What's the issue with electrons? Unstable. Can we produce or consume electrons? No, they have to be reacted and removed from the equation. This equation is not properly balanced, which means I will go back to my half reactions and adjust the coefficients within those half reactions so that when I add the 2 equations together, how many electrons do I see in my equation? 0. I didn't have enough time to do all that, so we'll do that again on Thursday. All right?